Okay, so in this example, we're given that a container is divided into two compartments, one containing hydrogen and the other one containing nitrogen gas, initially at the same temperature, but their pressures are different. And then we also calculate the Gibbs energy of mixing. Then we're given the initial and the final conditions of the system. And if we just quickly analyze this, initially the total pressure is 4p, but after doubling the volume, then the pressure will drop to 2p. You can get that from, I can't remember if it's Boyle or Charles's law, but one of those two will give that to you. And then, of course, their partial pressures you calculate from the number of moles. So 3 moles, the total number of moles is 4 moles. So there's 3 moles, so 3/4 of the pressure must be incorporated to corresponding to the hydrogen, and then 1/4 of the pressure must be corresponding to the nitrogen. So their partial pressures are calculated from that. So I don't necessarily have to give you the final situation. You can infer it from the initial conditions. But anyway, so you might be tempted to start with just to calculate the Gibbs energy of mixing directly, using the equation down below here. But the problem with this equation is it assumes that the two gases are initially at the same pressure and temperature, but they are the same temperature, but they're not initially at the same pressure. Of course, the hydrogen is at a pressure of 3p and the nitrogen is at a pressure of 1p. So we can't use this equation. So we will need to look at a way of calculating delta G in a very old-fashioned way. In other words, first calculating the initial Gibbs energy and then the final Gibbs energy, and then just subtracting the two values from one another. So sort of like we did in the derivation itself. So if we look at a point of equation 418, then the initial Gibbs energy of one gas is just equal to its number of moles times the chemical potential, the standard chemical potential of that gas, times RT ln of the pressure of that gas. So that's before we assume anything about the pressures of the gases being equal. And then in the same breath, so that's like G initial of one of the gases. And the initial pressure of both of the gases, so just that is the sum of, in the separate case, so separated, is the sum of both of them, both of these quantities. So ln P, we can call it ln P, we don't call it anything, plus in B, so I can actually call this the pressure of gas A plus NB times the chemical potential plus RT ln the initial pressure of B. I don't know how explicit I should be, but you get it because this is the initial condition, so it's the initial pressures of A and B that we are referring to in this. Alright, so this is how we can calculate the initial pressure of our situation. But we can also use this equation, of course, to calculate the final pressure again. So we don't necessarily have to, so we can use it to calculate the final Gibbs energy as well. So just again, the number of moles of A times its chemical potential plus RT ln, of course, of the pressure of the gas A. But now it's actually the partial pressure of the gas A, of course. So maybe we should use like a, I don't know, a prime to just indicate that, and then so we just don't confuse ourselves. But anyway, plus RT ln. Right. So this is our two situations that we have. So Now we just can. So now we have not a problem, but I mean, you might say, okay, how do we calculate the chemical potentials? Well, how I like to approach these kinds of things are that luckily you're going to subtract GI off from GF. So in this case, you should be able to realize that you are going to eliminate both the chemical potentials. You're not going to really have an issue with them. So you're not going to have to calculate them at all. So that's really the beauty of something in physical chemistry. Sometimes you just need to start out and look and see where you end up, and then at the end you can say, oh, maybe I need to find another way of dealing with this because I actually need this, and then you can do something else. But don't ever threat until the end. So now I can say that's not going to be a problem here. But anyway, so it's not going to be a problem. And then we have all the pressures, because we have the initial pressures, it's 3P and P, and then afterwards it's 3 over 2P, so 1.5P and 0.5P. So we can do something about that. You'll see it actually works out quite nicely. Okay, so let's start by calculating the initial Gibbs energy. So the initial Gibbs energy is, for the hydrogen part, it's 0.3 mole, or 3.3 mole, and then it's the chemical potential for hydrogen, plus, just going to leave in the RT part, and then we have an initial pressure of 3P, right, plus then 1 mole for the nitrogen part, its chemical potential and its pressure, of course, is just P. And the final Gibbs energy is again equal to, so that's again 3 mole for the hydrogen part, its chemical potential and now its pressure has changed to its partial pressures. In other words, let's write it as 1.5P or 3 over 2P or whatever you would like to write it as, plus the 1.0 mole for the nitrogen gas, and its partial pressure is 0.5 mole P. Okay. So all we basically have to do now is the Gibbs energy of mixing is equal to, well, GF minus GI. So we can, let's write everything out, I mean, nice explicitly. So I'm going to drop the 3.0 mole, I'm just going to write 3 throughout, so 1 whatever. So just going to do that, so it makes it a bit easier to see. So we have, for the final part, we have 3 mu H2 plus 3 RT ln 1.5P plus mu N2 plus RT ln 0.5P minus 3 H2 minus RT ln of 3P minus 1, so that's, we don't have to write a 1, mu of N2 minus RTP. Okay, so there you can see all the mu's are going to cancel, because mu N2 is going to cancel with mu N2, minus 3 mu NH2, 3 mu NH2, so then we're just left with Um, a very small RT lin part. So let's just count up all the RT lins. So we have what? Okay, we don't have. They don't have the same lins things here. So let's group them together first. So then I'll show you what we're going to do. So we have 3 RT lin 1.5p plus RT lin 0.5p, and then minus RT lin 3p minus RT lin of p. Okay, so now remember, the lin of something plus the lin of something else, the lin of something minus the lin of something else can be the lin of that divided by the lin of that. So what I think would be prudent is if we group this in a way, yeah, this is going to be good. Okay, so I think I maybe lost, where's the other 3? There should be another 3 RT here. It's the one that corresponds to 1.5. 1.5 and 3p should be, yes, so there should be 3 RT. Alright, so let's group the 3 RTs together. Right, so the ln of 1.5p minus the ln of 3p is the same as the ln of 1.5p divided by 3p. Alright, and then we can group the other two together, because the ln of 0.5p minus the ln of p is the same as the ln of 0.5p divided by p. Aha. Then our p's will cancel, and then we will get 3RT ln a half, yeah, plus RT, oh, I forgot the ln here, ln, so ln a half, or, I mean, just to make it a bit easier, 3RT ln of 2, so that's minus ln of 2 minus RT ln of 2 is then equal to, so then we can subtract these two, so that gives us minus 4 RT ln of 2. Yeah, and remember this is 4 moles, so let me just write that out again. So that's minus 4 mole, 4.0 mole, because I dropped the 0. Then R is 8.3145 joule per Kelvin per mole. T was 25 degrees Celsius, so it's 298.15 Kelvin. And then we have ln of 2. Plugging all that in a calculator gives us a value of minus 6.9, so that's rounded off, kilojoule All right, because of course 4.0 mole is two significant figures. So great, and that's of course spontaneous, so I mean, that makes sense. Okay. So that's a lot of writing work, but it's, at the end of the day, it's a very simple, it's actually a very simple example. It's not really that difficult. Just some algebra. And algebra is easy. Just have to grind through it. And not make little errors. Or if you make little error, just ensure that you pick it up. Okay. Yeah. That is it for this example. Of course, I will write it out nicely and neatly in the notes, but this is like the full written out way of doing it here. So